So this is our first video notes lecture, and what you're going to want to do while you're watching this video is pause every now and then when you need a little more time to write, and feel free to move backwards a little if you need to have a moment to listen again to what I'm saying, or if you just need that additional time to write. So make sure you're using all those tools. Also, don't forget at the end of the video to answer check your knowledge questions on the Google form, and that'll be sent to you through your Gaggle email. But in Unit 1, we're going to be looking at scientific thinking and connections in biology. For this first set of notes, we're going to be on page 5 of your handbook, and we're just going to be looking at the first 2 pages. So 1.1, this unit is mainly going to address what is science. What are we studying, and how do scientists study the world around them? So science is not just a collection of facts, concepts, and useful ideas, but it's a method of investigating nature and discovering reliable knowledge. And that's one of the key points there. Reliable knowledge is knowledge that has a high probability of being true because it has been justified by a reliable method. Now, when we talk about it being justified, we mean that it's been tested over and over again, and we've collected a lot of evidence that allows us to believe that this, what we think is a fact is true, okay, or this theory should be true. There are 3 critical components to reliable scientific thinking, or critical thinking. And so when we think of science and all the experiments that we have to go through, well, there are 3 other factors that come into play. The first is the use of empirical evidence. This is evidence that you can experience. And so that's an easy way to help you remember. Empirical and experience. Things that you can experience, or evidence that you can experience, could be things that you can see, that you can hear, that you can touch and taste. And these are things that can be repeated over and over again. If you think to one of the main laws of science, if we're thinking of gravity, well, you can take this orange and you can just drop it over and over again. And every single time I let go of this orange, it's going to drop, and that's going to be repeatable. And that's going to be different from what's known as circumstantial evidence, or testimonial evidence, or even authoritarian evidence, things that only happen in certain situations, or evidence just because someone told us it's evidence. The second critical component is the practice of logical reasoning. And this means you're going to carefully analyze your evidence. 2 types of reasoning are known as deductive reasoning and inductive reasoning. With deductive reasoning, you're going to draw conclusions based on your evidence. Every time I drop this orange, it's going to fall. There must be something causing it to pull down, or causing it to move towards the earth. Inductive reasoning, we're going to expand on our conclusions. So what is causing this to fall? What is this force that's causing it to fall? So what we have is our empirical evidence. We have to have evidence that we can see, hear, touch, taste, things that can be, most importantly, repeated. And you'll want to put a star by that it is repeatable evidence. And then we have to be able to reason with our evidence. Think about what our evidence is telling us. We have to draw conclusions, and we should also be able to expand upon that evidence. And then the last critical component is going to be the use of skepticism. And skepticism, or being skeptical, means that you're constantly questioning your source. Where did you get your information from? Where did you get your data from? And the reliability of it. And this means that you're really going to you're going to hold your beliefs to be tentatively, meaning that you're not going to believe right away what you see, but you're going to take a minute to think about it, reason with it, and decide whether or not you have the evidence that you need, or if you're going to need to collect more evidence. So looking at this picture right here, this is actually explaining to you how does science work. We have the testing of ideas, and notice that we have these 3 outer circles here, exploration and discovery. Notice that it's moving back and forth. We're going to explore or experiment over and over again. We're going to have a community analysis and feedback, constantly thinking about the data that we've collected and how we're testing it. And then we have our benefits and our outcomes. What's it going to mean if I believe that this is true? And then when we're thinking of science and how we're collecting data and what are we going to do with that data, well, that's going to lead us back to the scientific method. And the scientific method is going to collect data using the critical analysis traits that scientists value. So the 3 traits that we just talked about. First thing that you need to do when you are going through the scientific method and trying to collect this reliable data is that you're first going to have a problem or a purpose. And notice that in our diagram it says make an observation. Where do we normally come up with our problems? Where do we normally come up with our questions? From the things that we see. So, for example, if I saw a cactus growing in the desert, or a flower growing in the sun, then it leads me to believe, well, does it have to be in that sunlight? Does it have to be growing in that type of temperature? And so then, after I have my problem, or I've made an observation, I'm going to be able to ask a question. And a lot of times this is going to lead me to do a little research as well. Okay? I can look into where do those plants usually grow? How much light do they really need? How much light do they get on average? So for my example here, we have my research. I can look up hours of light in the desert. So I have this cactus growing in the desert. I am able to look up how many hours of light does the desert usually have. And then I get to form my hypothesis. Your hypothesis is going to be this formula for this question that you're trying to answer. And a lot of times we're going to write it in an if ... We'll write IV, independent variable, then ... dependent variable. And notice I'm putting that in parentheses. It says if ... IV, comma, then ... dp. So to give us a little more about what those things mean, IV is going to be your independent variable. Your independent variable will cause a reaction. Then your dV, your dependent variable, is going to, and we'll write that down, dependent variable can be changed or experiences a change because of our independent variable. So I'll repeat that again. IV means independent variable, and this usually or potentially could cause a reaction. Your dV, your dependent variable, is what can be changed or could possibly be changed. So in our example, if we're looking at this plant that's growing in the sun, I can say, for my example, if the cactus gets less hours of light than normal as my dependent variable, getting less light, lights being the independent variable, then it will not grow at the same rate. Okay. So again, my independent variable here would be the hours of light. Okay, that's something that I, as the scientist, can change. And then my dependent variable, well, what's going to be affected by those hours of light? Then it will not grow at the same rate, and that will be my dependent variable. And then after you've actually set up your hypothesis, you now can conduct an experiment. You can, so here you will experiment and collect data. One thing that we want to keep in mind here is that you'll need a control group. And your control group is the plants or whatever organism you're using with normal conditions. It is going to be used to compare. So in every good experiment, or any good experiment, you're always going to have a control group, and your control group is your dependent variable, whatever your organism is, a plant or an animal, and you're actually going to give it the normal conditions, because then you'll be able to compare it to what you're changing. If I have a cactus that I'm experimenting with, and it has the normal, let's say, 10 hours of light, then I'm going to have that there with the 10 hours of light, and I'll use it to compare it to the cactus that I've changed the amount of light to 4 hours of light, and I can compare the two and see if the rate of how it grows has changed at all. So again, you'll conduct your experiment, you'll collect your data, and once you're done doing that, you'll be able to analyze and then accept or reject your hypothesis. Okay? Accept or reject your hypothesis. If it turns out that I don't really see a big change in a plant that has less hours of light, then I reject my hypothesis. If it turns out that I have an extreme difference in the amount of growth, maybe it didn't grow at all, whereas the one with the normal hours of light did, then I can accept my hypothesis. So with this, we'll go over this a little bit more tomorrow, but most of us have already been through the scientific method and have already talked about these different steps. But the last thing I wanted us to look at is going to be looking at what is biology and what do we study in biology. So biology is a science that is divided into disciplines that examine different components of the natural world. Biology is the study of life. The smallest unit of life is a cell, and I'm going to put a big star by that because you absolutely have to know that. And some groups of organisms are multicellular, made of more than one cell, and consist of things known as tissues, organs, and organ systems. So the cell is the smallest, and you can get larger, becoming tissues, organs, and then organ systems. And you might want to pause for a minute. And in order to understand cells, we will need to know what they are made of. Everything living and non-living is made of matter. The smallest unit of matter, I'm going to put a star by this, is an atom. And multiple atoms are held together by bonds to form both small and large molecules. An example of this would be water. water. And water is H, 1 atom of hydrogen, and 2 atoms of oxygen, 2O. So here you have 3 atoms making 1 water molecule. And that's all for your notes today. Make sure you go back and get all the notes that you need.